When studying the different types of stresses individually, maximum allowable stresses are usually given to calculate the factor of safety. The factor of safety was most likely defined as the maximum allowable stress over the current stress for either normal or shearing stresses. Just like with yield failure criteria, or what is usually called ductile failure theories, covered in a separate 10-minute video, linked below, for brittle materials, the factors of safety can be defined in terms of the properties of the material instead of just some theoretical maximum allowable stress. It was the yield strength for ductile materials, and it will be the ultimate strength for the fracture failure criteria for brittle failure theories today. Most brittle materials have an ultimate tensile strength that is different to the ultimate compressive strength, although there are some exceptions. For example, cast iron can have an ultimate tensile strength of 30 kSi and an ultimate compressive strength of 110 kSi. For all the fracture criteria, the maximum normal stress brittle Coulomb-Mohr or modified Mohr will use the information that we get from Mohr's circle, specifically the principal stresses. If we try to categorize the different cases for the principal stress values for Mohr's circle, we would have two negative principal stresses in case 1, a negative and a positive principal stress in case 2, regardless of if the center is positioned on the positive x-axis or in the negative x-axis, and two positive principal stresses in case 3, where sigma A and sigma B are the two in-plane principal stresses, and sigma A can be greater than sigma B or vice versa. The first failure criteria states that a component will not fail if neither principal stress is higher than the ultimate strength. Positive principal stresses should not be greater than the ultimate tensile strength, and the absolute value of negative principal stresses should not be greater than the ultimate compressive strength. Remember that the ultimate compressive strength is usually a positive value, since it's a property. Using the numbered nomenclature we explained and used in the ductile failure video, linked below, the max principal stress sigma 1 should not be greater than the ultimate tensile strength, and the absolute value of sigma 3 should not be greater than the ultimate compressive strength. It also states that the factor of safety can be calculated as the ultimate strength over the maximum principal stress, tensile for positive and compressive for negative, whichever n is the lowest. Since principal stress A is not necessarily greater or lower than principal stress B, stress envelopes are often used for all the failure criteria. We have the value of sigma A in the x-axis and sigma B in the y-axis. The stress envelope that represents the maximum normal stress failure criterion looks like a shifted square, where the positive values are equal to the ultimate tensile strength and the negative values are equal to minus the ultimate compressive strength. If we assume that sigma B is in fact larger than sigma A, we would find all of our three cases on the top left side of our square, with cases 1, 2, and 3. If we choose to label our principal stresses with sigma A being greater than sigma B, we would find our three cases for Mohr's circle on the bottom right of our stress envelope. Looking at the stress envelope, what the maximum normal stress failure criterion tells us is that if both sigma A and sigma B are positive and smaller than the ultimate tensile strength, the component will not fail and the factor of safety would be the ultimate tensile strength over the highest principal strength, in this case sigma B. If both principal stresses are negative and neither of them are larger than the ultimate compressive strength, the component will not fail and the factor of safety can be calculated as the ultimate compressive strength over the absolute value of the highest negative compressive stress. Finally, if one of the principal stresses is negative and the other one is positive, we would compare the negative principal stress to the ultimate compressive strength and the factor of safety would be the lowest of the two, in this case N1. In general, regardless of if you're using the stress envelope, the overall factor of safety remains the same. Either SUT over sigma 1, the highest of the three principal stresses, or SUC over the absolute value of sigma 3, whichever factor of safety is lowest. The Coulomb-Mohr criterion for brittle materials changes the restrictions for case 2, for when one of the principal stresses is positive and one of the principal stresses is negative. We already know that when looking at the principal stresses, tau or the shearing stresses are 0. So the only stresses that we're going to see in our stress element are sigma B and sigma A. Let's suppose for a minute that we're still using cast iron that has an ultimate tensile strength of 30 and that our principal stress sigma A is equal to 29 ksi. We know that sigma A is cutting it close, but it's not quite greater than the ultimate strength. So if we follow the first failure criterion, the maximum normal stress, we would conclude that this component is not going to fail. However, the Coulomb-Mohr criterion takes into account that other negative principal stress. As we pull in the y direction with 29 ksi, the horizontal dimension of the stress element is going to want to shrink, which will only be exacerbated by sigma B also contributing to it shrinking. Of course, it's not about the strain or the horizontal component shrinking, but that horizontal stress is in fact adding up and pushing that element towards failure. This can be graphically represented if we look at an equivalent Mohr circle for the tensile and compressive ultimate strengths and define that failure will occur if the current stress Mohr circle is not bound by the diagonal lines and the circles. So if our principal stresses yield a positive and a negative value, even though none of them are exceeding the ultimate tensile or compressive strengths, there's still a chance that our Mohr circle would not be contained by the geometry in orange. This is represented in our stress envelope as a diagonal line in the second and fourth quadrant, the quadrants that correspond to case 2 of the Mohr circle. If you pay close attention, the factor of safety will still be defined as the ultimate strength over the maximum stress if both of them are positive, or the ultimate compressive strength over the magnitude of the largest negative stress if both of them are negative. In the case where one of them is negative and the other one is positive, we need to do a little math for the equation of a straight line. The slope, which is rise over run, would be SUT over SUC, and the y-intercept would be SUT. If y, which is sigma b, should not be greater than the value given by that straight line, and x is sigma a, we can divide by SUT to find that sigma b over SUT minus sigma a over SUC should not be greater than 1. And therefore the factor of safety can be calculated as 1 over the difference of the fractions. Notice that I did this derivation for the second quadrant, where I'm assuming that sigma b is greater than sigma a. In general, we know that the positive stress, sigma 1, should go with the tensile strength, and the lowest stress, which could be negative or 0, which is sigma 3, should go with the compressive strength. Most importantly, notice that this expression also works for quadrants 1 and 3, because if both in-plane principal stresses are positive, for example quadrant 1, sigma 3 would be 0, and the factor of safety would be SUT over sigma 1. If both in-plane principal stresses are negative, sigma 1 would be 0, and the factor of safety would be SUC over minus sigma 3. So it does work for all quadrants. Finally, the modified Mohr failure criterion is the criterion that comes closer to the experimental results that you get when testing brittle materials. And it's simply a combination of the previous two criteria, where you have SUTs for positive principal stresses, SUCs for negative principal stresses, and the diagonal line goes from minus SUC to minus SUT. The math for that diagonal line is almost identical. The slope will be SUT over the difference between SUC and SUT, and a y-intercept b that can be found by projecting that same slope for an x value of SUC. If we substitute y and x, and once again assume that we want to stay within that line, we can divide by SUC, factor out the properties fraction, move it to the left, and isolate 1 to find that the factor of safety is equal to 1 over the left-hand side. Knowing that we want to compare negative values to the ultimate compressive strength, we can substitute sigma A and sigma B by sigma 3 and sigma 1 to generalize it for the three principal stresses sigma 1, 2, and 3. As opposed to the previous expression of the Coulomb-Mohr criterion, this expression doesn't work for all areas of the stress envelope. We usually only use this expression if our in-plane principal stresses lie within the shaded area. For example, if both in-plane principal stresses are negative, we keep comparing the ultimate compressive strength to the highest negative stress. If both in-plane principal stresses are positive, we keep comparing the ultimate tensile strength to the highest of the positive stresses. And we also do this for when one principal stress is negative and the other one is positive, and the magnitude of the positive stress is higher than the magnitude of the negative stress. In this case, the factor of safety would be SUT over sigma b. To put everything we've learned into practice, don't forget to check out the links in the description of this video. There, you will find 2-minute examples for each one of the failure theories, as well as the 10-minute videos of the main topics of the Mechanics of Materials course. So make sure to check those out. Thanks for watching.